Let R be the region in the first quadrant. Okay. So, first quadrant is this one right there. Bounded by the graph y equals natural log of quantity 3 minus x. For 0 less than x less than or equal to x less than or equal to 2, R is base of a solid for which each cross-section perpendicular to the x-axis is a square. What is the volume of the solid? Okay. That's a lot of information. I don't understand. Okay, so it looks like we have some sort of solid. Looks kind of like this. So this will be when x equals 0, natural log of 3. And it goes on to 2, which will be, natural log of 1 right there. Natural log of 3 minus 2, which is natural log of 1, which equals 0. And we have squares that we're making, and we add them all up. And so I'm trying not to think too deeply on this one. So we're going to go from 0 to 2 of, let's see, the area of a square is width or length? I'll say width squared, and then we're integrating along the dx. So we know that the length slash width slash height is natural log of 3 minus x. So I'll do natural log of 3 minus x quantity squared dx. Yep, I can believe that. And I have no idea how to solve this. No idea. Maybe. So I think we could say that u equals 3 minus x, du equals negative dx. And that gives us something like natural log of u negative du quantity squared. And then I'm not quite sure how to do that. I think we could do like an integration by parts and then just kind of churn our way through it. But no, that's not. Like, I have a pretty strong aversion to using the calculator. I'm like, if you can get y by without using the calculator, gosh darn, dang it, you should. And that's not like a moral principle type view. It's just that every time you push buttons on a calculator, it raises your risk of making an error. And what's nice about these problems is if you get an answer and it's not one of your allotted answers, then you probably made a mistake and you can redo it. Probably. But that takes a lot of time to redo a problem 3 times. So I'm generally against using calculators. But in this case, nope. I think that's the easiest way to go. Calculator on. RAM cleared. I love this. Coolest app ever. More of a Casio guy myself, but this is cool. I'm not saying this redeems Texas Instruments, but this is cool. Okay. So we'll do, I don't know, natural log, maybe a parentheses, maybe a ln, maybe a 3 minus x, minus another parentheses, and maybe a square. And our window will be from 0 to 2, because once we get past 2, then we start taking natural log of values less than 1. And I don't want to do too much of that. Let's say 4 to negative 1. Nope, we'll do negative 1 to 4. Where's the delete? Here's the delete. Don't think I even need to do that. Okay. Graph. See what happens. Okay. So I think... Did we square that? Oh, and I messed up. Yes, we squared it. Okay. Good. I was worried I'd have to redo the drawing and the such. Okay. So now we're just going to do the integral from 0 to 2. So slow. So slow. This is another reason why I avoid calculators. Just the pain of having to hold down this arrow button. Wonder if there's a way to make it go faster. I should look into that. Yes. Yes, I will. Meh. My brief viewing, search of the Google, maybe. Couldn't find it, gave up. Hope, hope. Okay, we're getting close. We're getting close. Almost there. Now back off one just to not tempt fate. Okay, enter. Come on, give me a value. Give me a good value. One that's a possible solution. 1.029. Yes. Boom. Yes. So then this is our solution. So, man, I feel like I did that problem and I understood nothing. Okay, so to backtrack, let R be the region in the first quadrant bounded above by the graph, this, with 0 less than or equal to x less than or equal to 2, where R is the base of the solid. So we know it's a square, so the area of a square is going to be length of a side squared. We're going to evaluate it from 0 to 2 along the x-axis, so dx. And then basically we're like, all right, evaluate this integral. It doesn't seem to be an easy way for us to do that manually. So we're like, all right, calculator, magic. And we put it into our calculator. We make the window a reasonable size. We do second, evaluate integral, start at the beginning, go to the end, press enter, and it gives us the value. And it approximates the value of that integral. And that approximation is good enough for us. And that's how you do this kind of problem.